In this video, we're going to look at how to differentiate vectors on the general process of differentiation with a couple of examples. Okay, it's very familiar it's really just the same as differentiating a function of a single variable. It's just that we're going to do that for each component, as you'll see shortly. Okay, so let's say we have some object moves on this curve here. Okay, the position vector points always at different points in time t, or for whatever the variable t stands for, whether it's time or something else, okay, will give us our position of an object on this curve, or just a point on this curve. Okay. Alright, so point P has this position vector r of t. P lies on the curve here. Q lies on the curve here. It has position vector r of t plus h. Alright. And so what we're going to do is we want to find the derivative. Okay, we want to find how the vector changes. So, all right, so position vector in 3 dimensions is x as a function of some parameter t, may or may not be time, in the I direction, plus y of t in the j direction, plus z of t in the k direction. In any other number of dimensions too, we'd only have x and y. If it's in more dimensions, then we're going to have higher numbers of variables, w, x, w, k, j, whatever. Okay. Now, our derivatives will be expressed r dash of t will be the limit as h approaches 0 of r of t plus h minus r of t all over h. Another way of writing that is d dt r of t, or particularly if you're working with time, you'd use the dot notation with the dot above the r of t, or v of t. It might be a velocity. Okay. What happens is you have a position vector at some point on the curve here, another position at a different point over here. What's the rate of change at the point P? Okay. This difference vector here, this one here, okay, is r of t plus h minus r. If we take this vector here, and if we add the negative of this one to it, like that, then we get a vector going this way, this one parallel to here. Okay, so it's the same operation. It's the same object, just displaced. All right. If you have a look at the diagram over here, in the limit as h goes to 0, this secant here, vector secant, becomes tangent to the curve, to this curve at the point P. It becomes this tangent to the curve at P. So it becomes a new vector tangent to this curve. All right, a new vector. And r dash of t is the limit as h approaches 0, r of t plus h minus r of t on h. Now that's handy because we can unpack that, moving down here a bit. Remember, r of t was given x of t in the I direction, y of t in the j direction, z of t in the k direction. So the derivative r dash of t, dr dt, v of t, or r dot of t, whatever you want to call it, is the limit as h approaches 0, x of t plus h minus x of t on h for the x component. Same process for the y component. Same process for the z component. And if there are more components, it would be the same again. This is just the definition of the derivative for a function of a single variable. All right? And so this here becomes x dash of t, this here becomes y dash of t, and this becomes z dash of t, each in the I, j, and k directions. And similarly, if we're in higher dimensions, the same result would carry on. Let's have a look at some examples now. If r of t is cos 2t in the I direction, plus sine 2t in the j direction, plus t in the k direction, let's find v of t, the velocity, the acceleration, a of t. Okay, you can imagine this is a particle traveling along this path or the curve defined by this vector, position vector here, and the acceleration at t equals 0. All right, well, the velocity as a function of time will be r dash of t. Well, that's going to be minus 2 sine 2t plus 2 cos 2t plus k. The acceleration, r double dash, will be the derivative of that, so that's going to be just another 2 out front, minus 4 cos 2t, and the derivative of cos will give us a negative and a factor of 2, so we have minus 4 sine 2t. This part constant here becomes 0. Okay, the velocity at t equals 0 is, well, sine of 0 is 0, cos of 2t, cos of 0 is 1 times 2 gives us 2, and we have the constant here, k. So what we end up with is 2j plus k, no I component. The acceleration at 0, so substitute t equals 0, and again we have minus 4i, because cos of 0 is 1, times the minus 4 here gives us minus 4i. Sine of 0 is 0, so that drops out. There's no k component, so it's simply the acceleration is minus 4 units in the I direction. Okay. 4 units per second if it's time or whatever. Okay, now prove the speed of the particle is constant for this particular situation. This is not always true, just in this particular situation. Prove the speed of the particle is constant. We're going to have here speed is the absolute value. Remember, velocity here, velocity is a vector. A vector has a magnitude, which is its speed, and it has a direction. We're after the speed part. In order to extract the speed part from the velocity, we take the absolute value of the velocity. Okay? So the absolute value of r dash of t, or v of t, okay, is the square root of each of the components squared and summed together. When we do that, we get 4 sine squared 2t plus 4 cos squared 2t plus 1. Well, that's an identity, so that'll be 4 times 1. Okay, which is 4 plus 1, which is 5, square root of 5, which is clearly constant. All right, that's true in this case, but don't imagine it's true in general. Okay, also, one thing we can find is that if r dash of t is dx dt in the I direction plus dy dt in the j direction, okay, that's r of t, just differentiating each of the components with respect to time, because the vector's been parameterized in terms of time. That's handy because for the Cartesian path that this describes, we can find the rate of change of y with respect to x. We can find the gradient of the Cartesian path by simply using the chain rule, because dy dx will be dy dt times the reciprocal of dx dt, which is dt dx. And so, handy way, if we know this component and we know this component, then we simply take this component and multiply it by the reciprocal of this component here. Okay, which is the same as this component divided by this component. And that'll give us the gradient along the Cartesian curve